I want to do an example of finding the electric field due to a continuous charge distribution. A distribution of charge in this case of a total charge plus Q spread evenly around this semicircular arc. The half circle is entirely above the x-axis, radius capital R centered at the origin. I want to find out what the electric field is at a position along the x-axis, a distance a away from the origin. So that's my question. What is that electric field? For any continuous charge distribution problem, I have a strategy that I always use for these problems. You can take shortcuts here and there, but really, if you follow this strategy, it'll always work. So let's spell through what that strategy is. Step one is always draw a picture. You've got to do that. The picture, I'm a very visual thinker. Physics, in my opinion, is a very visual discipline. So drawing a picture is a first crucial step for making this work. Step two, then, is going to be we need to divide this overall charge, this continuous charge, into a bunch of tiny little pieces, dq. So divide charge into pieces dq. In calculus speak, the d here means tiny little, so dq is a tiny little charge. And in particular, in our case up here, we're going to look at this and say, fine, I'm going to choose some, when I think about a dq, I'm going to think about just breaking this up in this line up into tiny little pieces. There's my dq. For this case, I've got dq as that tiny little piece, and you can imagine that I'm going to break this up into a bunch of tiny pieces. For other systems in 2 dimensions, maybe you'd split it up into things that weren't points, but points are great. The important thing about the dq is that you should know exactly what the electric field is for your dq. So in this case, my little bit of charge dq is essentially a point. If that's an infinitesimally small little piece of my arc, then it is essentially a point. And I can use Coulomb's law for that. Coulomb's law, recall, says that the d here again means tiny little. The tiny little bit of electric field due to my tiny little charge dq is equal to 1 over 4 pi epsilon naught. dq is my amount of charge divided by r squared r hat. I'm using ordinary r here. A little confusing here and there, lowercase r. But what I'm going to do, the ordinary r, I should draw that in my picture. Always draw it in your picture. R, the distance and the direction that are interesting here, are from the source point, the dq, to the measurement point, a. So if I draw that in, it's always the r that's important is this r right here. Here is r vector, as shown. So that's my r vector in this case, is going from dq to a. And in Coulomb's law, that's always the vector that shows up here. The magnitude of that vector is little r with no vector sign, and its direction is r hat. We'll say more about those in a minute. But I've done my step 2, dividing the charge into these little pieces. Step 3 in my strategy, in my standard strategy for continuous charge distribution problems, is always to ask, are there symmetries that will simplify our answer? Is there something where I know the answer has to be reflectionally symmetric across the x-axis, so there can't possibly be a y component? In this case, sadly, no symmetries here. This case has no symmetries that will help us say this. If I think about my answer, it's going to be the charge is sort of up here somewhere, so the net effect has to be down and to the right, kind of. There's not going to be anything that'll simplify. So no symmetries to worry about. So step 4 in my strategy for continuous charge distribution problems is always to write that little bit of charge in terms of geometry, the shape of our system. And when I say write it in terms of geometry, what I really mean is to find some label variable. This marker seems to be dying on me. I need some label variable that will uniquely label every little dq that I'm going to consider. In this case, I can think of two reasonable choices for a label variable. One choice could be to say, well, every point dq, every little dq along my arc has a unique value of x that labels that. And so I could say my x is going to go from negative r to positive r, and that's my x, and each x corresponds to a point up there. The other choice, the one I'm actually going to make, is to say, hey, let me choose an angle, call this angle theta, and my angles will uniquely label each dq rather, each little bit of charge around the arc. And this one I like better because I know that the charge plus q is uniformly distributed along the arc, uniform around there, and theta goes uniformly along the length of the arc. Each little theta, if I look at a little wedge of theta, each one of those will contain the same amount of charge if it's the same size wedge. So that theta will be a nice uniform, that theta matches the uniform distribution along the arc. The x, I need to do some much more complicated stuff to figure out arc length for a given value of x that varies from point to point. This is easy. I like the theta. So I've written this in terms of this, I've chosen a label variable theta, and to figure out how to write dq in terms of that theta, what I want to do, I want to say, well, okay, there are a lot of ways of thinking about it, but I'd say, okay, what fraction of the total charge is in that little dq? Well, I know that dq divided by total charge q is the fraction of total charge that's in there. Then I could say, what fraction of the total angle is in that little dq? And well, I could say that is d theta divided by my total angle. Always use radians, folks. My total angle goes from theta equals 0 to theta equals pi. So pi is my total angle. So that's just showing those ratios have to be equal. That's what it means to be uniformly distributed in theta, for the charge to be uniformly distributed. My tiny little q is related to a tiny little wedge of theta that I've chosen, a tiny little bit of angle. So in other words, I can say that dq is equal to total charge divided by pi times d theta. All right, so that's my step 4. I've written dq in terms of the geometry because now instead of dq, I've got this written in terms of theta. That's good. I've made progress. So step 5 in my strategy is then write that dE vector, my tiny little bit of electric field due to this dq, write that in terms of the same label variable. And in particular, in this case, what that means is I need to know what is r and what is r hat. What are those things? I need to identify those in terms of theta. And for this, I'm going to have to clear some space over here to do it because figuring out r and r hat always take a little bit of work. I know that my vector r goes from my source point to my measurement point. So I can say that, I guess I could say r vector in my picture, maybe I can make this purple to give me an excuse to get rid of this black marker that's dying. I can say that r vector is always going to equal r, the position of my measurement point, minus the position vector of my source point. That's always what this r vector is. I just vector math, source point plus this displacement vector equals measurement point. That's how we define the r in Coulomb's law. So r measured by r source, well, what is that? R measured, my measurement point is a really simple thing. In x hat, y hat, z hat notation, it's just a x hat plus 0 y hat plus 0 z hat. So that's my measurement point minus, what is my source point? I guess maybe I'm not going to have room in this little space. Let me put this on the next line down. Minus my source point. Well, it's just a point on the circle, right? This dq is at some xy on that circle of radius r, and I've written theta. This is a big trig thing, just sines and cosines. So in particular, it's going to be r cosine theta x hat plus r sine theta y hat. That's my source point, is just cosine and sine, radius r, standard thing. So subtract the two. In other words, writing this out, my r vector equals, my x hat component is going to be a minus r cosine theta x hat minus r sine theta y hat. There we have my r vector there. Now, of course, r vector isn't what I was looking for, right? I want the magnitude and the direction of this. So but once I have r vector, I can get those pretty easily. Let me clear some space over here. I've already defined these things. I don't need to keep it written. Once I've defined what r vector, or what my r vector is, then the magnitude of this I just get by the Pythagorean theorem. R, which is just the magnitude of r vector, is going to be the square root of the x component, a minus r cosine theta squared, plus the y component, minus r sine theta squared. There we have it. That's my r, my magnitude r, my distance. I can make this one tiny bit simpler, only a tiny bit, it's not really great. I can make it one tiny bit simpler by squaring this out and using a trig identity. Under that square root sign, I'm going to have an a squared minus 2ar cosine theta. And then here's where I get to be a little bit clever. R squared cosine squared theta will be the last term from squaring this, and r squared sine squared theta, hey, cosine squared plus sine squared equals 1. If you know only one trig identity, that should be the 1. This adds up to just be r squared, because I didn't need all that length. So that's my, I don't know if this is any simpler, but this is my distance r from the source point to my measurement point. Cool. As for r hat, by definition, the unit vector in the direction of vector r is just that vector divided by its own magnitude. And so here I can just write this down as, well, I mean, it's a mess, but I can write it down as a minus r cosine theta x hat minus r sine theta y hat all over the square root of a squared minus 2ar cosine theta plus r squared. If you're noticing, this looks like some kind of law of cosines deal. This is some kind of law of cosines deal. But okay, so r and r hat, I have them. Now I have all the pieces I need for my dE vector. Let me put that down. Let me just write down exactly what I get plugging in all the pieces to write dE vector in terms of the label variable. I get that dE equals 1 over 4 pi epsilon naught times, okay, dq is q over pi d theta. So I can put that in. I can say q over pi d theta. R hat over r squared. Well, r hat was already r vector over r. So putting it all together, I get r vector over r cubed. So I can write this as a squared minus 2ar cosine theta plus r squared. This is a little bit too big. Write that whole quantity to the 3/2 power in the denominator, and the numerator is going to be this thing, a minus r cosine theta x hat minus r sine theta y hat. I have this. That is the end of my step 5, because I've finally written the whole dE vector in terms of the geometry, in terms of the label variable theta. You can see the only things here are theta and a bunch of constants. A, for our purposes, is a constant. That was the point I chose to measure at. R is the constant radius. X hat and y hat don't depend on where I'm measuring things. Those are Cartesian vectors. So those are all constants. It's just that it's a d theta, and that gives me 5. That's my step 5. So hey, I'm nearly done with all my strategy here. Step 6, it turns out. Make sure I can see this. Step 6, it turns out, is do the integral. Do the integral. So in particular, that means that I should come in here and I should just say, cool, I'm going to integrate both sides. Integral dE is just the electric field. This will be the total electric field on this side. We're going to electric field equals, there we go. The total electric field is the integral of dE. This is just calculus speak, right? dE is a little bit of electric field. Integral means add up all the, and so add up all the little bits of the electric field, you get the total field. And on this side, I could put the integral sign here, but these are all constants. I can just do an integral sign here. My limits of integration are theta from 0 to pi. And I've got this integral. All I have to do is evaluate this integral, and I'm set. The bad news is that this is an example, like it turns out almost every example that exists, where doing this full integral analytically is impossible. Or, well, it's not impossible, but the result ends up being expressed in terms of elliptic functions, which is just a fancy name for we couldn't do this integral, so we gave it a name. And so you can write this down in terms of elliptic functions. The y component you can do analytically, it turns out, but without the x component, it's kind of boring. But the point is, you could throw this, if you had a specific value of a and a specific value of r, you could easily throw this thing, or even just a ratio, honestly, you could easily throw this thing into some kind of, Maple or Mathematica or Wolfram Alpha or something, and get a result for this integral, get some numerical result. This integral itself contains all of the physics that we need. All of the interesting stuff going on is built into this integral. I like that because it means with all the interesting physics built in, I'm done. There's math that I wish I could do a little bit more clearly, that I wish I could find a final answer, but the physics is done. The interesting part was setting up this integral, getting it put together, and actually evaluating it. That's a technical challenge of one sort or another, but that's all we have. So that's the final step. You do the integral. This is a closed form expression, well, not closed form, but it is an expression, an evaluatable expression for this integral to figure out what the total electric field is at distance a. Even though I can't do it explicitly, I can still do my step 7 in my strategy. The strategy that I tell students to do when they're solving these problems always has a final step. If it's possible in your situation, if it's relevant for your situation, try to check your answer by taking a limit and comparing to what your physical intuition is for what that situation should be. Take a limit and check your answer. So in particular, in this case, I'm going to take the limit where a is much greater than the radius of the circle. What's this mean? This means I'm going to go very, very far away and look at what the effect of that half circle is on my electric field at point A that's very far away from A. From that distance, I expect that it's not really going to be apparent that there's this little arc going on. That all I'm going to see is a total charge of plus q sitting over there. And so it should look kind of like a point charge. Conceptually, that seems right to me. So in this case, let's look at what we've got. I haven't been able to do the integral in general, but in this limit, when a is much greater than my radius r, I can look at this integral. I can say that my electric field is approximately equal to 1 over 4 pi epsilon naught q over pi integral from 0 to pi of d theta of, okay, the denominator, if a is much greater than r, the only term that's going to matter there is the a squared. So I've got an a squared, I guess. I've got my approximately equal here, so I get to do all sorts of crazy stuff. I've got my a squared in the denominator. In the numerator, maybe I care about this, a squared to the 3 halves. That's important. A cubed is my denominator. A squared to the 3 halves power is a cubed down there. And the numerator, again, if I'm looking at just the leading behavior, the only term in the numerator that depends on a is the first one, so that first term is going to be much bigger than either of the others. I can say this is approximately just a x hat in the numerator. Well, canceling those out, that's 1 over x squared. There's no theta dependence here. These are constants with respect to theta. So this integral d theta comes out to be just pi. And that means that this turns out to be, well, this pi cancels that pi, 1 over 4 pi epsilon naught q over a squared x hat. That's my approximate answer. And you know what's fun about that? This looks exactly like Coulomb's law for a point charge q, a distance a away in the x hat direction. And that is exactly what we'd expect. So that is a big check mark. Yes, it doesn't mean that this integral is proven to be exactly right, but at least it shows that the limiting behavior of this integral has the right limiting behavior. So I didn't forget some prefactor up front. I didn't have a massive blunder. I may have other minor blunders, but no massive ones. It's promising. So that is an example of solving a continuous charge distribution problem by integrating over some variable, integrating over all the little tiny dq's that make up that continuous charge to add up to the total electric field at some chosen measurement point. And even if you can't do your integral analytically, that's a math problem. I'm a physicist. The physics is done at this point. We have the physics we need, and